We are now going to continue with problem 7. These problems, of course, get a little more complex the more you do. So this one we have the integral of x times, in parentheses, 2x plus 1, and the parentheses are raised to the second power. Now in a few minutes we're going to do some problems where we learn to use a rule or a method called substitution, or the substitution rule. So for those of you who remember that, you might think this looks like a substitution problem. Although actually, if you tried to use substitution on this problem, it actually would not work. So really the only thing we can do here, as it stands now, I cannot integrate this. But like I said on the last problem, sometimes you can do some algebra things and rewrite or rearrange or make it look different so that you can then apply some rules. So how about, what would happen if I went ahead and multiplied out the parentheses? 2x plus 1 quantity squared is like 2x plus 1 times 2x plus 1. And most of you probably learned how to FOIL, that's what you called it. But anyways, if we multiply out those two parentheses, it ends up being 4x squared plus 4x plus 1. And what I'm going to do is, now, I'm going to take this x, since it's x times the parentheses squared, it's really x times all of this. I'm doing this to sort of save a step, because now I can rewrite my integral to look like this. So once again, this is where I've taken the initial problem, which I don't really know how to solve, and by doing some algebra, multiplying things out, I now have basically 3 terms, and I can apply the power rule to each of those terms. So this first one, add 1 to the exponent, divide by the new exponent. For 4x squared, the 4 tags along, add 1 to the exponent, divide by the new exponent. For x, add 1 to the exponent, divide by the new exponent, and then of course don't forget your constant. So basically, I don't even need to rewrite this, the 4's cancel out. So you're going to have x to the 4th plus 4/3 x cubed plus 1/2 x cubed plus c. Alright, let me check and make sure that's correct. And yep, that's what we have. I want to make sure I don't make any mistakes on these videos. Number 8. Integral of 2 e to the 2x plus 2 over x dx. Well, we have 2 terms, and if we look at each of these terms, this first one's an exponential, this next one has x in the bottom. But I believe I can actually integrate both of those terms. I know how to do it. So this is a matter of just using some of the rules we've already learned. 2e to the 2x, the 2 tags along, you copy down the exponential, and then if you have a number, a coefficient in front of your x, if you go back and look at your notes, the rule is that goes in the bottom. If I look back in the notes when we first did that, I don't know if we actually did an example, but if you have e to the ax, where a is a number, you rewrite, copy down the exponential, and it's multiplied by 1 over the number in front of x. So for this problem, it's really e to the 2x. The 2, right, it tags along. Then you write down, you copy e to the 2x, and then you look at the number in front of the x, which is 2, and it goes in the bottom. Now the integral of 2 over x, the 2 is just a coefficient, tags along. You could think of this as x to the minus 1, but then hopefully you realize, maybe you want to change it to x to the minus 1 and then use the power rule. Now if you try that very quickly, you'll realize all of a sudden you're going to be dividing by 0 again, and then maybe you'll remember this is that special case. Two over x is the same thing as 2 times 1 over x. What's the integral of 1 over x? Natural log of x. It's that special rule. So that should be the answer for number 8. Actually, obviously cancel those, sorry. So yeah, e to the 2x plus 2 natural log absolute value of x plus c. All right. Now these are getting a little more interesting the more problems we do. So now we're back to an exponential function. The integral of e to the 5x plus 3 with respect to x. Now the thing you have to realize is when we learned to take the integral of an exponential function, this was the rule. But once again, this only applies if you have a number times x. We have a number times x plus 3. So this, I cannot apply this rule as is written. So in class, we talked about problems like this, and the thing you can try is using substitution. Now let's hope it works. So it's always the same procedure. The first step is always, because what we're going to do is we're going to take this integral with a variable as x, there's a bunch of x's, and our goal is to substitute and replace all the x's with some type of variable u. And if we do it correctly and it works, what happens is, let me write it this way. So we have some integral with x's. We change it. We have an integral with u's. And then hopefully, we can then integrate it when the variable is u. And then the last step is, once we have the answer with u's, convert the u's back to x's, and then we've actually solved it. So this is called substitution. So the first step and the key is, what are we going to call u? When we have an exponential function like this, it's almost always the whole exponent. So we say let u equals 5x plus 3, and now substitution steps are always the same. You define u, then you always take the derivative, du dx, the derivative of u with respect to x. 5x plus 3, derivative of 5x is just 5, derivative of 3, a constant is just 0. So du dx equals 5. But because eventually I want to try and substitute or get rid of this dx, I want to take this little equation here and solve it for dx. In other words, to get dx by itself on one side. Normally a quick little shortcut is you can just swap these. And you end up with dx equals 1/5 du. So now, let's do my substitution. So my original problem had x's in it. E to the 5x plus 3, but now 5x plus 3 I'm calling u. So I can rewrite this as e to the u. And then dx I'm going to replace with 1/5 du. Matter of fact, the 1/5 I'm going to move out front right away. Since it's just a coefficient, it's a number. Now, if substitution works, at this point, we should have an integral that we can actually work out. And we actually do know how to take the integral of this, e to the u with respect to u. That's just the basic natural exponential integral. And the rule is, you copy down the exponential, you put 1 over the coefficient in the exponent, it's just a 1, there's no number there. So now, we've taken the integral with respect to u. Of course, we're not done yet, because the original problem had x's in it. We need the answer to have x's. Right now we're sitting here at u. So now the last step is switch from u back to x. And to do that, we go up to our original definition of u. U equals 5x plus 3. So let's go down here, wherever I have a u, replace it with 5x plus 3. So 1/5 e to the 5x plus 3 and that should be your answer. Let me check and make sure. Number 9. Yep. Alright, so that's the first problem where we do substitution. I think we might have a few more of these. Hopefully you won't find it too hard once you get the hang of it. The key is when you first figure out what u is. So number 10, the integral of 1 over 3x plus 5 dx. Now, we don't really have a rule to integrate this. I can't really split this up into separate fractions because I have 2 terms in the bottom. However, now here's where, this can be a little tricky until you do a few of these. You look at this and you say, well, I'm sort of stuck. Let's try and do substitution. Sometimes you try things in math and you don't know whether it's going to work or not, but you have to try it because you don't know until you try it. So we've been learning about substitution. Let's take this denominator and let's call it u. So now we take du dx. The derivative of 3x plus 5 is just 3. If I want to get dx by itself, so now if I do my substitution, 1, this 3x plus 5 is what I call u, then dx is 1/3 du. I'm going to move the 1/3 out front right away. And now I ask myself, can I solve this integral? And yes, I can, and hopefully you remember by now it's that special case where you have 1 over the variable by itself. Hopefully you remember the integral of 1 over u du is just natural log of u, natural log of absolute value of u. And now the final step is switch back to x's, so u is 3x plus 5. And there you go. So these substitutions, sometimes it's a little trial and error. Sometimes you try it not knowing for sure it's going to work until you try it. But if you're sort of stuck, substitution is often the key to solving it. Okay, these last few look even more complicated. Integral of 2x e to the x squared minus 1 dx. So it's almost like we have two functions in here. I obviously don't have a rule for this kind of integral, but I am going to try substitution. So you think, well, should I maybe call the x, call that u, or maybe the exponent to be u? You can try both. I think one of them you'll sort of get stuck. I think what might work is if we set the exponent x squared minus 1 equal to u. Now we go through our substitution steps. Take the derivative. Derivative of x squared minus 1 is 2x. I'm going to solve this thing for dx. Now here's the interesting thing. I am now getting ready to substitute. I'm going to move the 2 out front. I want to substitute. I've got an x and e to the x squared minus 1 dx. My goal is to get rid of all these x's. And I can, this x squared minus 1, I can replace it with u. I can get rid of the dx. Although I'm a little worried because the dx still has an x in it. But also the key thing is I've got this x here that I don't want any x's left, but I'm not sure what to do with it. Why don't we just for now let it tag along and then see if we can figure out later on how to get rid of that x. So let's just rewrite this x. E to the x squared minus 1 is e to the u. And then times dx. Dx is 1 over 2x du. So it's not really ideal yet because I do have u's here, but I've also got x's. But maybe you can see it. Turns out it's going to work out okay because look at my x's. I have x up here and 1 over 2x down here. The good news is those x's cancel. As a matter of fact, if I bring this 1/2 out front, 2 times 1/2 is 1. By the time I clean all this up, I'm left with the integral of e to the u du. And that's a pretty easy integral, right? You just copy down e to the u. There's no number coefficient in front of the exponent. Well, while it looked very messy, when I switched to u's, it became pretty simple. Of course, now the last step is to convert it back. So it's e to the x squared minus 1 plus c. All right. Wasn't as bad as I thought. Things worked out pretty well. All right, looks like a couple more of these indefinite integrals. Integral of 3x. All right, if you're looking at your review, which is square root of x squared plus 8. Just to save time, let me go and convert that to a rational exponent. We almost always do that. So once again, pretty messy. I don't have any rule that really applies to this. So I probably need to try substitution. Once again, usually when you have a choice, should I substitute for the x or for this parenthesis? Usually, if you choose the messier thing, sometimes that's going to be a good guess. So let's set u equal to what's inside the parentheses. Let's just go through our steps and cross our fingers and see if something works out. Derivative of x squared plus 8 is 2x. If I solve for dx, I get 1 over 2x du. Once again, I've got the x hanging around, which I'm not thrilled about, but we'll see if things work out. So let's do our substitution. Move the 3 out front. I've got this x again here now, which I'm sort of stuck with, so let's just write it for now and see what happens. X squared plus 8 is u. So u to the 1/2, then dx down here is 1 over 2x du. Now once again, maybe God is smiling on us because I'm not really happy. I'm going to be sort of stuck if I can't get rid of these x's, but I have x in the top, x in the bottom. They cancel out. Let me move the 2 out front. Basically, it simplifies down to 3/2 times the integral of u to the 1/2 du. Now this is a power rule. I can integrate this. Remember, add 1, so 1/2 plus 1 is 3/2, and then divide by the new exponent. Of course, now I need to simplify this complex fraction, and our little shortcut is, you've got a fraction here, you can multiply the top by that reciprocal. And this is sort of nice, 2/3 times 3/2. They cancel. So when you come down to it, u to the 3/2 plus c, and now if I replace u is x squared plus 8. So it's x squared plus 8 raised to 3/2 plus c. All right, once again, substitution worked out. And the last one. Integral of 2x to the 4th over x to the 5th plus 1. Derivative, or the integral with respect to x. I can't really simplify this. I can't split it up. I can try substitution. About, let's take that whole denominator. We'll set u equal to x to the 5th plus 1. Now sometimes, if you tried to set u equal to x to the 4th, you can go and try it, and it may work out, it may not. If it doesn't work out, then you come back and you set u equal to the other one. I think my hunch is this is a better choice. That's why I did it. If you do enough of these, sometimes you start to see what you're trying to do. So this is 5x to the 4th. If I solve for dx, 1 over 5x to the 4th times du. So now substitution. First of all, the 2. X to the 4th, I'm sort of stuck for now. X to the 5th plus 1 is my u, but dx is 1 over 5x to the 4th times du. Now the nice thing is when this substitution works, even though you have x's, they need to cancel out, which they do. Bring the 5 out front. Hope you recognize the integral of 1 over u. It's not the power rule. It's that special case where it's a natural log of absolute value of u. Substitute back in for u. U is x to the 5th plus 1. 2/5 natural log. X to the 5th plus 1 plus c. I believe that's correct. All right, so those are all the what we call indefinite integrals. So the keys are, we use the power rule a lot. A lot of times you have to take integral of some exponential functions, that 1 over the x, which becomes a natural log. And then a lot of times, as the problems get more complicated, we have to try and use the substitution rule. All right, let me stop now, and I have the last 5 are these definite integrals. And I'll do these on the next video, then we'll be done.